Okay, so we just saw symbolically how one of these product rules works. And what I want to do now is actually verify sort of computationally exactly what's going on here. So we have two vector valued functions, u and v. And what we're going to do is we're going to verify the product rule for the dot product by computing both the left and right hand sides of that rule. So in order to get started, let's work with the left hand side. So what we have to ask ourselves is, well, what do we actually compute? So on the left-hand side here, this is telling us we need to take the derivative of u dot v. So the first thing that we should do is actually find u dot v. So this is not particularly hard. We have two vectors. We know exactly how to take their dot product. We'll multiply those first components together, multiply the second components together, and multiply those last components together. It's not particularly difficult. All right, now this is just a legitimate function of t. We can take a derivative of it pretty easily. So when we compute the derivative of u dot v, all we have to do is take the derivative of each of these terms. I want you to notice that there's actually a product in each of these terms, so we're really going to have to use this product rule for functions of a single variable. When we differentiate this first piece, we'll get an e to the 2t plus 2t e to the 2t. It's just the product rule on t e to the 2t. The second piece here, derivative of the first is 2t times sine of 5t plus the first, t squared, times the derivative of the second, which is going to be 5 cosine of 5t. And then for the last piece, which I'll write under here, derivative of the first is 3. And then the first times the derivative of the second, we'll have a 3t plus 5. And to differentiate the logarithm, it's not bad either. We just take 1 over the inside of the logarithm, and then we multiply by its derivative, which is 2t. Okay, so this is how we compute the left-hand side. So take a second, make sure that you know what's going on here, and then we'll look at the right-hand side. All right, so now that we've computed the left-hand side, let's look at the right-hand side. So for the right-hand side, we have to do a slightly different computation. We have to take the derivative of u and dot it with v. And then we have to add to that u dotted with the derivative of v. OK, so when we do that, our u prime dot v plus u dot v prime, we first take the derivative of u, which isn't too bad. It's just going to be 1, 2t, 3. And we're going to dot that with v, which is e to the 2t sine of 5t log t squared plus 1. And to that, we're going to add u, t squared, 3t plus 5, dotted with the derivative of v. So that's going to be a 2 e to the 2t, 5 cosine 5t, and a 2t over 1 plus t squared. OK, so that's a much longer expression that we have to calculate, but the dot products now are very straightforward to find. So this first one will just give me an e to the 2t plus 2t sine of 5t plus 3 log t squared plus 1. When I calculate that second dot product, that'll be a 2t e to the 2t plus 5t squared cosine 5t plus 3t plus 5 times 2t over 1 plus t squared. All right, so now let's compare this result to the one that we just got. So we have an e to the 2t here. We have an e to the 2t right there. We have a 2t e to the 2t there, and we have a 2t e to the 2t there. We have a 2t sine of 5t here. We have a 2t sine of 5t there. 5t squared cosine 5t, 5t squared cosine 5t. 3 log t squared plus 1, 3 log t squared plus 1. And this last term is the same as well. So these two expressions are equal for this specific example. So we've verified that the derivative of this dot product does satisfy the product rule that we had on the previous slide. The one thing that I do really want to emphasize here is that this is not a proof of this specific dot product formula. We've just shown that for these very two special functions, this result holds. In order to actually prove these rules, we have to do it the way that I did in the previous video, which is to show that this holds for all functions in general, not just two. All right, so we just verified the product rule for the dot product in the last example. And after seeing that example, you may have actually asked yourself, well, why do we even care about these product rules? When we actually used the product rule, it was a lot harder than first computing the dot product and just taking the derivative. So why do we even care? Well, as it turns out, the product rules are much more useful in more theoretical or more abstract contexts. And such a context is in this example. So here we have a differentiable vector valued function, and we know that the magnitude of r of t is e to the 2t. And we're now tasked with showing that r and its derivative are not orthogonal for any value of t. So we don't actually know what r of t here is. We only know one property about it, what its magnitude is, and we have to somehow use that to show what we need to show. So the first thing to note here is we want to show that r and r prime are not orthogonal. So what we really need to show is that if we take r and we dot it with its derivative, we never get 0. Or we don't get 0 for any time t. So we have to get a dot product involved here somehow. And we need to get a derivative involved somehow. So the trick to this problem is actually realizing that the magnitude of this vector is actually somehow related to taking a dot product. And so, simple little fact here, for any vector v, if we look at the magnitude squared, this is the same as just taking the vector dotted with itself. So I'm not sure if you've seen this before, but there are a few ways to show this. I'd say if you're not comfortable with this right now, the two ways that come to mind to show this, you can either write out both sides here in terms of the components, v1, v2, and v3, or you can use the fact that v dot v would be magnitude of v, cosine of the angle between them. Cosine of the angle between them is 0, so v dot v will just be magnitude of v squared. If you're not comfortable with that, take a second and pause the video and just try to work this out for yourself. Okay, so hopefully you're now comfortable with this fact, and now we can actually use this fact. One great choice for a vector v here is this vector valued function r of t that we were starting with. So the nice thing here, we can say that the magnitude of r of t squared, on one hand, it's just r of t dot r of t. On the other hand, we know what the magnitude is. It's e to the 2t. So the magnitude squared will be e to the 2t times e to the 2t, which is e to the 4t. OK, so now we have something that's much easier to work with. Now what we can do is take the derivative of both sides, and that's going to introduce our r prime of t. So we're going to take the derivative of both sides. On right here, we're going to use our dot product rule to say, well, this is just r prime of t dot r of t plus r of t dot r prime of t. On the right-hand side here, we'll take a derivative and we'll just get 4 e to the 4t. Now when we look at this, what do we know about dot products? Or in other words, how does r prime dot r compare to r dot r prime? Well, hopefully you remember the dot product is symmetric. It doesn't matter what order we take them in. So this left-hand side here is actually just twice r of t dot r prime of t. The right-hand side, of course, is 4e to the 4t. And now if we divide both sides by 2 here, we see that no matter what t is, r dot r prime is 2 times e to the 4t. Well, can that function ever be 0? Hopefully you remember that the exponential is always going to be positive, so this does not equal 0 for any time t. So what does that tell me? Well, that tells me that r of t is not orthogonal to r prime of t for any t. So here's a good example. We actually didn't work with a real function for r of t. We were tasked in this problem to say no matter what type of function r of t is, as long as its magnitude is e to the 2t, it can never be orthogonal to its derivative. So in order to do this, we had to rewrite the magnitude of r in terms of a dot product and use the product rule for differentiating dot products. And from there, the solution wasn't particularly bad. All right, so just to explore a concept behind that last problem a little more, I want you guys to think about this question. If we know something about the magnitude of r of t, does that tell me anything about the magnitude of its derivative? So I want you to think about that for a second. Don't think about it in terms of symbols, but think about what this actually is asking us to do conceptually. So when we have curves, especially in R3, we are forced to pick a parameterization of those curves. And so this r of t is going to describe a curve. The magnitude of r of t will describe how far that is from the origin. So here's a question. What is magnitude of r prime of t going to tell us? Well, that's going to give us a measure of the speed at which the curve is traced out. So there are many, many, many ways to parameterize a curve, and there are many, many, many ways or different speeds that we can trace that curve out. So just because we have a curve doesn't tell us anything about the speed at which we trace it out. So my general impression from thinking about this is that no, if we know what the magnitude of r of t is, it doesn't really tell us much about the magnitude of the derivative. And so to explore that in the context of a specific example, here's a true-false question. If the magnitude of r is constant, is the magnitude of the derivative 0? So I want you guys to take a second and think about that for yourself before I answer it. All right, so this is actually something that we see on exams all the time. Is this statement true? Well, no, it's not. If magnitude of r is constant, maybe you can actually sort of think what type of curve that could be. It would actually wind up being a circle. But one way that I can convince you explicitly that this is false is I'm going to give you an example of a function, r of t. If you realize that this thing is really describing motion in a circle, then hopefully what I'm picking for a function is not going to be too bad. We need a radius 4. And on the inside here, I'm just going to put in omega. If you've taken a class in physics before, you can think of this omega as an angular speed. Otherwise, just think of it as a number that I put in there for whatever reason. So here's a way to parameterize a circle of radius 4. And to convince you of that, let's actually compute this magnitude. So this magnitude is not too bad. We'll square both components. We can pull out the 16. And if we do that, we see our familiar Pythagorean trig identity. And so this is just square root of 16 because this guy is 1. So we get 4. So yes, this is a function that no matter what t is, the magnitude is 4. So now let's actually look at what r prime is. So r prime of t is not particularly bad to compute here. It's just minus 4 omega sine omega t, 4 omega cosine of omega t. And we can compute the magnitude. The calculation is very, very, very similar to the one directly above it. We square both components, add them together, use that Pythagorean trig identity, and at the end of the day, we're going to get 4 times omega. And here, we're going to assume that omega is a positive constant. Otherwise, you get 4 times the absolute value of omega. So make sure that if you don't understand where that computation comes from, make sure that you actually do it yourself. But I want you to note here that the magnitude of r is 4. The magnitude of r prime is actually 4 times omega. We could pick any number we want for omega, 5, 13, pi, or my favorite number, 17. And we have found an example of a vector-valued function whose magnitude is always 4, but the magnitude of the speed is anything we want it to be. In fact, we can even go a step further here, and we can say that if you instead let this r of t be 4 cosine of, why just restrict ourselves to a constant times t inside of there? We can actually look at a function of t inside of there. If we do this, we can actually show via the same steps that we've done up there that this magnitude is still 4, and that the magnitude of the speed now actually winds up being 4 times omega prime of t. So even if the magnitude is constant, the speed at which we trace out that circle could vary. It doesn't have to be uniform like it was in the example we just worked. So the big point with this is, just because we know something about the magnitude of a vector-valued function, we know nothing about the magnitude of its speed.